just want to tell you about a piece of research we did here over the last couple of years. Professor Johnson Cole was the originator of the idea. He was based down in Bournemouth, had the idea that if this worked in the mirror box, how about using a computer instead? So what he did was, he got movement sensors, which we attached to people's remaining legs. And if you move your remaining leg up and down, or if it was an arm, you move your arm across, whatever remains of it. And on the screen, we generated an image, which was either an image of an arm coming across, grasping an apple, or a leg going up and down, hitting a drum, making a beat. And this image appeared on the screen, and it appeared crudely like your own image of your own body on the screen. So it wasn't like you were sort of standing behind yourself looking. It was like, as it were, you were actually in the car if you ever play on those sort of games with children or grandchildren. Personally, if I go on those motorbikes at the service station on the motorway, if I go on those game motorbikes, I'm on that motorbike straight away. I completely enter into it. And some people do seem to enter into this very easily. So we put people through this to see what happens to them. We brought 14 patients through, 7 arms and 7 leg amputees, and 5 of each group felt completely embodied into the leg. So in other words, the leg they saw on the screen, as they moved their own leg, felt like their own leg. And they started to describe getting sensations from the legs of them. So there are various words for this. I've used the word embodied there, that they became embodied on the image on the screen. Some of them reported quite significant reductions in pain, and they felt that it was their arm and it was less painful. So I put a quotation of one of the people there, said, when I move the avatar's arm, in fact, it does not tingle, pain disappears into the background and merges into the movement sensation. Of course, there was no movement sensation, it was just the image on the screen. The carryover effect we didn't study, but one of the patients has told me in clinic since then that it lasted for about 6 months. That was just on one treatment, lasting about an hour. If anybody's interested, that's the paper. It's not a particularly sparkling paper, but that was the paper. So I'm going to hand over to Tamar now, and then if you want to ask me any questions later on, I'm happy to answer.
Hi, can everyone hear me?
Yes.
So my name is Tamar, and I've done my PhD at the University of Jerusalem in Israel, hence my exotic accent. I'm not a medic, I'm a researcher, I'm a neuroscientist, and I've been doing a lot of work to try and learn how our hands may affect our vision. And I think my research might have some really interesting consequences when it comes to upskilling amputees. So what I thought I'd do is I'll show you a bit of my previous research, which is considered basic research. It doesn't necessarily have any direct implications on patients. And once we've gone through that and you've got to know my line of thought, I could tell you a bit about our future research. And we would love to take ideas. So it's true that we have ideas, but we would love to get some more. So we'd be very happy to get your responses. So if you look at the space around your bodies, it would look no different to you than any other bits of space that are further from you. But the space around us, and particularly around our hands, is the theatre for our interaction with the environment. So it is within this action space, space and everything else, where we could use our perception, which is what we see, what we hear, the touch we feel, in order to guide our actions, which is how we move our body. So, for example, in the spirit of the World Cup, if someone would throw a ball at me, I would use my vision, my eyesight, in order to recognize that the ball is approaching me, getting near me, approximately where it is going to appear, and I would use that visual information in order to change the posture of my body in order to kick it, or in my particular case, probably avoid it. So we can think about lots of different examples how we're using information about the environment, sensory information, to guide our actions. But I would like to present to you today an opposite view. So it is because within this action space, this space around us, that there's this tight link between perception and action, that I believe that our possibilities for action within this space may actually affect our perception. So David has demonstrated to you how visual information of the body could affect our sensation of where the body is, which is something that we call the body schema. I would like to show you that where our bodies are may affect our perception and visual perception in particular. So this view that perception is made for action and our possibilities for action would affect our perception generates a few interesting hypotheses that I've been studying. For example, we can claim that if within action space perception is made for action, then our perception and the way our brain responds to stimuli within our near space, within our action space, should be fundamentally different than any other representations of space that are away from us. Another interesting hypothesis is that if my possibilities for action would change, let's say if I've lost my hand and can no longer respond with it or interact with the environment with it, this would lead to some changes in my perception, for example, in my vision. So before I would show you my results, I would like to introduce to you a method that I've been using in my research, as well as many, many other neuroscientists in order to study the human brain. And this method is called functional MRI, and it is based on the same technology as MRI. So MRI is an acronym for magnetic resonance imaging. And you might have come across these machines at hospitals.
At the front.
Okay. Yeah. I am a neuroscientist. So you have these great big magnets with a hole in the middle. And what we do is we stick people in this hole. It could be patients, it could be subjects. And using this magnet, we're able to take pictures of the inside of the bodies and brains. And the pictures would look very much like what you get when you take an X-ray or a CAT scan, but unlike these methods, magnetic resonance imaging does not rely on ionizing radiation, so it is perfectly safe for use. It doesn't have any side effects, so that's why it's become very, very popular, both in research and in medicine. So MRI allows us to look at the different structures in the brain and infer at the different tissues. So basically, we can learn about the anatomy of the brain using this method. And this has become very useful in order to learn about the human brain. But if we really want to understand how the human brain works, and if we want to be able to characterize its function, we need something more. And that's why functional MRI is being developed. So functional MRI, or for short FMRI, allows me to infer at any given moment which parts of the brain are being active. So if, for example, I would like to study how Homer's brain responds to donuts, all I have to do is stick Homer in one of these MRI scanners, present to him a donut or an image of a donut or the smell of a donut, and see at the same time which part of his brain become more active. And if I'm a really good scientist, then I would also show Homer in different times, also scones or bagels, and would make sure that the areas that I've identified as the donut areas respond more strongly to donuts compared to other puddings or brown chips and so on. Okay? So if you're wondering how this method works, it's actually based on a very simple physical property of red blood cells.